Today's video is the second part in the series on chiller minimum flow control. Last week we spoke about the fundamental control strategy of the bypass valve and the pump and what controls where, which is the main part of this series. In today's video we're going to talk about the process variable to the bypass control valve. So the bypass control valve is controlling the flow through the chiller. Now, in last week's video, in the example, we mostly spoke about the flow being in liters per second, and I think the example that we used was controlling to 10 liters per second. Generally, we don't have magnetic flow meters on the chillers, but we do have them on large projects. But you are quite likely to have a differential pressure transmitter across the chiller's evaporator. So in this video, we're talking about the selection of that pressure transmitter, which is often incorrectly selected, and it causes a controls problem in that bypass control loop. So the first thing that goes wrong with that pressure transmitter is if the project manager is ordering the pressure transmitters or all the instrumentation for the chiller plant room, and he knows he needs a pressure transmitter for system pressure control. I don't know why I keep looking there, but and he needs two pressure transmitters, one for each chiller for the evaporator. And what can happen is when he's placing the order, and he knows from his experience that we normally have, say, a 0 to 250 kPa pressure transmitter on the system pressure, sometimes the project manager will just order 3 of those. So 3 boxes arrive on site, and they're the exact same range, 0 to 250 kPa. One goes in system pressure, and the 2 get installed across the evaporator of the chiller. Now, the obvious problem is there that the chiller's design flow is around, let's say for this example, 50 kPa is the design flow, and the minimum flow, let's say, is 25 kPa. So the bypass valve is modulating to maintain at least 25 kPa across the evaporator, which equates to the minimum flow to the chiller. So you can imagine if we have a 250 kPa pressure transmitter over the evaporator and we're controlling to 25 kPa, it means that the pressure transmitter is going to measure a 1 volt DC signal from a 0 to 10. So your analog input to your controller is going to be measuring a 1 volt process variable. And that is not good, because generally we should select instrumentation so that we're controlling to the mid-range of the pressure transmitter. So we're controlling to around 5 volts DC, 6, 7, 8, 9, 10, but we're not controlling around 1 volt or half a volt. And that, actually thinking that through right now, if the system pressure was around 250 kPa, which is a reasonable number, then actually we should have somewhere around a 0 to 500 kPa pressure transmitter for system pressure. If we have 0 to 500s on the chiller, then we're actually going to be controlling to a signal much less than 1 volt DC, maybe half a volt DC, somewhere around there. That's really poor control, considering that evaporator pressure control is probably one of the most sensitive control loops in the building. If we're controlling temperature or pressure or humidity, CO2, condenser water temperature, all those things, if they fluctuate a bit, it doesn't matter. It'll just the control will adjust or get back to set point. But in this case, once you go 5, 6, 7, 8 kPa below the control, we're at like the cutout. So we need to have really good control and a good signal into our BMS. So that's the first part of this issue, when somebody orders the same range sensor for the minimum chiller evaporator as they do for the system pressure. So sometimes when I'm diagnosing chiller issues and we're looking at, is it controlled the right way around, I always take a walk to the plant room, go to the pressure transmitter, I look on the side, and I have a look what is the range, because that's normally a good indication if there's going to be a problem or not. So now, the next part of this discussion is sometimes the BMS designer or the person selecting the instrumentation knows that they can't use that pressure transmitter. So most of the case, it's not as bad as that 0 to 500, but what can happen is the BMS guy says, right, well, the chiller design is 50 kPa. So we select a transmitter, for 100 kPa, so that 50, the process variable, is in the middle of the range. So we select a 0 to 100 kPa range transmitter. Now that is a lot better and will probably work, except that we're not controlling to 50 kPa. That's the design flow for full load. We're controlling, at a lower point, so we're controlling at 25 kPa. So even with the better selected transmitter, we're still controlling to around 2.5 volts of the range of the transmitter. Now 2.5 volts will probably work. It's okay. I don't think that's going to be an issue. But the point here is, A, are we choosing completely the wrong sensor range? And B, if we're actually considering the pressure sensor range, let's get exactly the right pressure sensor. Like let's have so it's like a 0 to 50 kPa sensor, and we control to 25 kPa, we're square in the middle, we're gonna have good control. Now, occasionally the BMS guys challenge me on this, and they say, look, Bryce, that's fine, it makes sense. However, if we choose a pressure transmitter with a range that's quite low, when we are at design, the pressure transmitter can go unreliable because it's reading a value higher than its full range. Well, that's probably correct, but I don't care if it goes unreliable because the bypass valve is not controlling the design flow rate. So I don't care if the input goes unreliable. Write some software there so that it doesn't freeze the loop or cause any drama. But I don't care if it's unreliable and then dips into being reliable and then comes down, and then we start controlling. So think about the range of the pressure transmitter that you're selecting. Now, just quickly again before we go, this will be a short one. Ideally, we should have flow meters and not pressure transmitters. I know it's difficult to get over the line because it costs more money. But if you've got a project that you really want to get good energy efficiency out of, and you want to have, a good turn down and really get some good variable flow to the chiller, so that when you're in low load and the valves are closing off, we can slow the pump down, and have good reliable control of the bypass. Us getting a magnetic flow meter in there would really help with that. Like the pressure transmitter will work, but it's a bit jumpy, it's not as good. So, of course, as BMS guys, we can't influence this component, but just think about it and understand that that would be a better thing to have. So if the consultant specified flow meters and mechanical contractors trying to value engineer them out and take, a $5,000 flow meter out and put a, $500 pressure transmitter in, maybe just say, hey, hang on a sec, guys, like we can do that, but there's a knock-on effect. There's going to be a knock-on effect of that. So let's, try and stick with the flow meter, try and sort of defend the consultant's design. And try and reduce the amount of value engineering. Well, that's it, guys. Hope you learned something there. Like usual, like and subscribe. Thanks for watching, and I will see you next time.